1, 2, okay. Hello to you all. I have to admit I'm a little nervous. That's my first talk in English, so excuse me if you don't understand something. If I talk too fast or you don't understand, please tell me. Today's talk will be about embedded devices, hacking embedded devices. I'm into it for about 2 or 3 years from now. I'm hacking mostly routers, but techniques that I will show you are applicable to most of IoT devices, because most of them are just small system on chips with Linux on it, which we can hack. So what's first? I think hacking embedded devices is all about connecting and hacking serial console. So for those who are not familiar with serial console standards, please, you may know RS-232, RS-422, and these others, and also you will find something called UART. So what's this? The thing on the left is the device, is a hardware device for transmitting, for doing serial communication. So just basically a chip that is able to communicate with serial. Thing on the right, the RS-232 and the others, these are so-called standards. So they specify what electric characteristics, what voltage levels, and what the transmission cables is all about. So, not to confuse, don't confuse UART and RS standards. So, briefly about the RS, which we will not need. RS-232 is the most popular. You can find it in all old computers, PC, and it's all about modems. So it's just a standard to connect to modem to computer. Besides standard transmission pins, there are also signals that are very specified for modems. For example, RE is ring indicator. You have also some hang-up pins and others. Voltage on the RS-232 is very high. It can go from plus 15 volts to minus 15 volts. So it's a lot for embedded device. And as I will show you later, you never connect RS-232 to embedded. The other 3 standards are somewhat similar. They have another electric characteristics. They were designed for long links, so like this one can be as long as 1.5 kilometers, so it's a lot. All of this was used in the 80s or 70s maybe for accessing mainframe machines, because there were no computers at home. You had only modem and connected by terminal to your mainframe. The standard on this one is much used now in some access control systems. It can connect a point to multi-point device and have communication between all of them. So that's all about RS. Let's go to our embedded devices. We will never see 15 volts or more on our embedded. So let's have a look what voltage we can found. We can basically have two types of electric circuits: CMOS and TTL. One is transistor based, other is MOSFET. They are not. It's not really important. What the important thing is voltage level, because when you are connecting something to system on the chip to the processor, they are not voltage tolerant. So if you connect 5 volt to chip that has 3.3 volt, you will burn it. So this table shows you what are voltage levels for serial connection. This is this is bit 0, the upper level, and the down is bit 1. Lower VOL is voltage output low. It's the voltage level that chip is outputting when it wants to send 1. Voltage input level is the maximum voltage that chip will interpret as the logical 0. And the same is for VH. So voltage input high is the minimum level of voltage that needs to produce logical 0. Voltage output high is the maximum voltage the chip is outputting to send a 0. So and of course, if chip sees voltage in these areas, the state is undefined. So we can have 0, 1, or nothing. What we can see from this, there are some devices that work in 5 volts CMOS logic level, but you will not encounter they frequently. They are rather rare. Most of the devices are operating on 5 volt TTL or 3.3 volt TTL voltage levels. So as you can see, all these levels, all these voltages are in the same level, and you can easily connect devices from 5 volt TTL to 3.3 TTL without any risk. But this is only for serial console, because if you will try to connect some other signals like GPIO, I2 E2C or some others, you will definitely burn your chip. Okay, so and the other one, 1.8 volt, this is getting popular now. And as you can see, it's incompatible with any of these standards. So if you want to connect this kind of device, which may be some Odroid or maybe something else, you will need a logic level converter. This is this is very simple device. It's from SparkFun. It's easy to use. If some of you know electronics, you can build your own very easily. How this works, we have a high voltage side, we have a low voltage side. Some of the low voltage side we connect, for example, 1.8 volt chip on the upper 3.3. RX, TX input output. And this pin is for connecting reference voltage. So here we connect 1.8, here we connect 3 or 5, and we have bidirectional communication without burning anything. How we connect? We can have a serial adapter. The one that people like the most is based on FTDI chip. It's really feature-rich. It's not only serial adapter, but you can have many other protocols like SPI or even others. It's also the most expensive. There are other cheaper serial adapters like this one or this one. They are quite okay. They can have troubles with some hardware. I've seen hardware that doesn't work well with some of these cheap devices, some of these cheap adapters. So if you encounter one of these problematic hardware, you should try something else. Like Raspberry Pi is an ideal serial adapter. It's operating on 3.3 volts, very stable. You can have 2 serial devices connected to it, and also kind of fun is using ESP 8266 for serial. There is this example sketch in the Arduino that you can use to create a gate, like Wi-Fi, serial to Wi-Fi gate. It's working this way: that ESP connects to the Wi-Fi, opens telnet port, and if you telnet to it, you basically see the serial output that is connected to a chip. So it's quite handy. If we have serial adapter, we need to find a console, which may or may not be problematic. On this picture, console is rather straightforward. We can see 4 pins. We can assume this is console. How to find it? First, we need to find a ground pin, which we can, for example, with multimeter, try to reference voltage from, I don't know, chassis to the ground pin. We also will have a voltage pin. It may not be connected, and transmission and receiver pins. On this picture, situation is a little bit harder. We are not sure if this header or this header is serial. What can we do? There is a method using a multimeter. It's based on the fact that when device is booting, it's outputting some text, some boot messages on the console. So if you connect ground to ground and voltage meter to one of the chips that will be transmitter chips, and boot your device, you will see voltage floating and then stopping floating. So it's quite handy way to find serial. Of course, you can also find specifications of your processor. You can find where the output serial is and look where it is connected on the board. How we connect? This is easy. TX to RX, RX to NX, ground to ground. Never connect power. So NC is no connect. 3 volt, no connect, or you will fry something. When you found the console, you need to find the baud rate. Most of devices operate in 112, 100,000, 15 to 12 bit baud rate, like this one. If you are not sure what the baud rate is, we can try some popular ones, or we can use this tool that we can switch through the baud rates and see and easily establish what the proper baud rate is. Other parameters are basically not needed, so this is quite easy. What we can see when we connect to the console, the first thing we see is bootloader. So bootloader can be U-boot, DOS U-boot. It can also be Redboot or some others, but U-boot is the most popular. I think if you open any of your Chinese cameras or some other stuff, you will find U-boot in there, maybe slightly modified. It's a free software, so all the partners that are using their own U-boot has to release sources, which is very nice because it allows us to better understand and play with hardware. These are the architectures. So as you can see, it can run on almost everything. If you are into routers, there is a very popular modification of U-boot made by PP from OpenWrt project. It is very cool because it has some options, for example, for web upgrade. So if your system upgrade went wrong and you don't have system anymore, you can use rescue booting on U-boot, which has a web interface. So you don't have to use serial console or telnet. So 2 words about flash layout. it's the second thing that you will see. Basically, in embedded devices, you will mostly find some anti-D-flash. This is flash device is divided into partitions. So the first partition is the U-boot, the bootloader. And then you have some other partitions, for example, with firmware kernel, some config, and with the root file system. So how U-boot works, how it is booting? First, we have very small ROM code that is embedded into system of the chip. That its only function is to find the loader of the U-boot. So it has some very simple procedures like look for flash or look for an MC card or an AMD card, where it tries to load the secondary program loader, the SPL. U-boot is divided into two parts. First is SPL, which is very small, so the ROM code can load it. Second part is the full ELF image of the U-boot, so the actual program. So ROM finds SPL, and SPL loads the rest of the U-boot. And after U-boot, we are booting Linux kernel. So if you want to hack a device, U-boot is the best place to do it, because it's rarely locked, especially in the cheaper devices. This is example of a booting from my Qubit truck. This is non-standard version of U-boot. It's more like you can find in Android or a tablet. But even there, we can see some information. These are, here we can see what are partitions, bootloader, rootfs, and some udisk. We can use it later to prepare another firmware. U-boot has some shell. Also, between version of U-boots, you can find some that are compatible with USB devices, so you can even connect USB keyboard and work with U-boot with it. It has a help, so you can look for the commands. They may vary between various devices. Here, for example, this is fastboot. People familiar with Android will know fastboot from smartphones. It can load files from ext. It can also modify memory, and the rest of commands. There are a lot of other commands to work with. The most important thing is U-boot is environment. Environment is basically a set of parameters that is used to boot system. So here we can find baud rate, which U-boot is using to communicating, some standard command to boot. This is bootm. It means boot from memory at this address. Here is image, some environments, and this is rather complicated script that tries to find and set parameters for loading kernel. Here we have a root partition. This is ND on this device, and some other stuff. So we can write it down and also use it to play with U-boot. So when we are in the U-boot, we're gonna need some image to run on it. So my weapon of choice is OpenWrt, because it has very large list of compatible hardware. I will show it on the end, and also because its build environment and ecosystem is really nice. So building OpenWrt is rather easy. You clone a repository, you update feeds. Feeds are external progress, because OpenWrt is like a plain system with Linux kernel, BusyBox, and some standard commands and programs. If you need anything else like web server, telnet daemon, or web interface, all of this can be found in feeds. So this is the commands: update list of feeds and install them so they will be available on the build. This is not straight. When you are building OpenWrt, you need to do 2 times many config. So in the first step, you set only target system, which is architecture, CPU, subtarget, target profile, and target images. Target profile is the device, the name of the device that we are building. Target images are a format of images. So by default, it will build only SquashFS firmware to be written to Flash, but we will need a RAM disk image. So this is image for booting OpenWrt from RAM without installing anything to Flash. So we choose the target system, we exit miniconfig, then we need to make a dev config, which will set all the important packages and all the important parameters of the build. Then we can enter miniconfig the second time and choose some packages that we want to build into system. And of course, after this, make VS is for verbose. It's very handy because the build will fail. It's very easy to fail a build. For example, the most often case that the build fails is when the build image is bigger than Flash on the device, or is bigger than RAM that we have. So please don't put Python interpreter or GCC in the image, because it will simply not build and not run. After complete build, which will take some time, we can find 3 types of firmware. First is the most important for us. It's initramfs UImage bin. This is image that can be used to boot directly from RAM, so without installing. 2 other images. Factory is it's a firmware file that is installed directly to Flash from original firmware that was on the device. And sysupgrade, it's another image. Sysupgrade is only for upgrading OpenWrt. So if you install OpenWrt on your device and want to upgrade it, then use this image. If you are installing for the first time, you use this. And if you only want to boot the system, you get the first one. Okay, so what can we use to transfer firmware image to the device? How can we run kernel? Because from the U-boot, we often will not have access to Wi-Fi controller. Often the device doesn't have Ethernet ports. So the only method that we have is using a very ancient file transfer protocol. This was popular in the 80s, probably, for transmitting files between modems. The first one, X modem. It's really old, from 77. Y modem is some upgrade, is some better version of the X modem, and Z modem is the newest one. It's from 86, and it is quite mature, it's quite a good protocol. It works on the serial console, so you can transfer files by using only your serial port. Of course, it is very, very slow. If baud rate is about 10 kilobytes, you can imagine how long will it take to transfer 3 megabytes of image. It will take forever, like 20 minutes or more. So how do we use it? We need to build the OpenWrt image first, and then from the U-boot, we are using command loadb. Loadb is loading binary image from serial port with Kermit protocol. On your computer, use ckermit, which is a client for Kermit, and with these simple steps, you finally send the firmware. Firmware is loaded into this address. You have to look which address is correct for your hardware. That's why I put this into this. You can find it in the initial U-boot loader or from the print-env command. And when the image is loaded, you can boot it by using bootm, which is boot memory command. So with these commands, we can, if you know architecture and we have correct OpenWrt image, we can boot our board, we can boot our device and use the system to hack it further. If your U-boot doesn't have the loadb command, which can be possible, you should use loady. It's Y modem protocol, and there is a just different command for sending files. But it's possible too. So, when you have system, you have of course a root prompt, and you can look around what's, for example, what's in rootfs, in the original rootfs of the device. In procentd, there is a partition table from the MTD device. You can use it to download specific things, or you can download whole firmware from dev MTD device. It will just put you the whole flash. If you have network, like when you booted OpenWrt, you will have your Wi-Fi card, so you can connect to Wi-Fi and transfer files with SCP. If you don't have it, you can use Kermit and wait forever for the transfer to complete, but it's quite possible. So, when you have a firmware, we want to analyze it because we need to split it into parts. There is a very nice tool called binwalk. This is binary walker. It is a program that tries to find signatures of the bootloader, kernel, root file system, and other stuff in the image, and tries to extract them into files. So this command will extract everything that you will find. There is also another switch parameter for extracting recursively, but this is in most cases all we need. If we are not sure what the firmware is, or we think if it's encrypted or compressed, we can also do an entropy analysis and just look how the entropy in the file is looking. So, what will output binwalk? This is the starting point. This is like offset in the image file, in decimal, in hexadecimal, and this is signatures and things that binwalk read from it. So, as you can see, this is probably some ubiquity router image. We have some headers, and on the 3 to 4 byte, we have a U image, which is basically the kernel. Later there is some LZMA data, we don't know what it is, and here we have partition header, also not needed. This one is the most interesting. This is where the squash FS file system starts. So this is where all the files, all the system the device has in it. If you are not familiar with the Squashfs, it is very simple, compressed, read-only file system. It needs two partitions. One partition is for read-only data, and the second partition is mounted like an overlay, and is used to read for writing data, like changing configuration or something. But it's not used in system upgrade. When you upgrade your system, you just overwrite the whole Squashfs. Okay. You can, when playing with firmware files, you can often find the Squashfs file system which you can't unsquash with two unsquashfs. It's because device manufacturers are sometimes modifying the Squashfs, so they use non-standard compression, or they just change the headers, so it is harder to extract. There is a great tool named Sasquatch. It just tries to extract file system in every possible way that it knows. There is also other tool, quite older, called FMK, Firmware Modification Kit. And in this other tool, you can find like 20 or 30 versions of the tools used to pack and unpack firmware files. But I think that this is much better because it really could extract files that no other program could do. So if your Squashfs doesn't unsquash, use Sasquatch, and it will help. Of course, sometimes you will need to use your hexadecimal editor and by hand analyze and modify the headers of the Squashfs. So, what the most simple technique to modify firmware? I'm talking firmware modification, like for example, you have this cheap China camera that has a default password on it and Telnet daemon, which you can't change. So you don't want to install your own firmware. You want to just shut down Telnet daemon or change a password or whatever. Most simple steps is just run OpenWrt, try to download the firmware, extract files, and modify file system. Then you should use all the files that was from extraction, like the headers, the U-boot, some non-standard files, and just glue them in the way that was original, and upload it to the device. This is possible because Squashfs is the last partition in the flash layout, so it can be a little longer and nothing will happen. Like addresses for the loading kernel will stay the same. So, okay, this is for modifying original firmware. If you want to install your new system, then you just run your OpenWrt and use the sysupgrade command to install the whole system to the device. This is when you want to have like newer kernel or some stuff that wasn't available in original firmware. How to flash? Some slides before I was showing you how to run image from external source. This is very similar. There are just two additional steps. First step is erasing flash. Of course, you should find your own address and the size of the flash that you want to erase. This is needed because these simple flashes, flash chips, you need to erase before you can write to them. So this is why this command is needed. The rest is almost the same, only before booting. you use cp.b. .b means binary copy. It means that sizes and offsets are in bytes. There is also cp.w, which is for words, and .l, which is for longs. Binary is the most handy. So here we are loading image into the memory, and here we are copying image from the memory to the flash, and this is the size, and then we just boot our image from flash. And of course, if we don't have load B, we can always use load Y. So where to go from this? If you found a device that you can't hack with U-boot, so for example, its U-boot is locked, or you just can't access it, you have some other possibilities that are a little more dangerous to use. The first one is connecting directly to the SPA flash. So you can have your FTDI adapter or some Raspberry Pi, and you can very carefully connect directly to the chip that have flash image in it. And then you can download firmware. You can also overwrite it. It's not very safe, but I haven't seen devices that was bricked in this way. So writing directly to the flash chip is always a possibility. If you don't have this possibility and you have the hardest way, which is using the JTAG port. Everything must have JTAG, so you can be 100% sure that you will find some JTAG pins on your board. They may be not easy to find, but it should be there. And if you have it, you just connect your OpenWrt, run the processor, and use commands quite similar to this using in U-boot to write flash or read it. If someone is interested in this, on this page there is a whole process of debricking a popular router using JTAG, and there are all of the comments and on the pins that you should connect. And of course, if you are interested in this and have some more questions or some projects, you can write me. So that's all from me. Maybe you have some questions, and I will have some answers. So wait a second for the microphone, please.
1, 2, 3, 4.
Okay. So to sum up, first of all, I've got to have the image of OpenWrt, right? Mm-hmm. Then yeah. I'm loading into the device, yes. And then I'm performing all the commands.
Yes.
Okay. So that was, for me, it was unclear, maybe for the others.
Okay. So the OpenWrt image you can build or you can download from the site. If the device, device is not compatible, you can always look for some generic images. So if you have a generic image, you will not have your network adapter or some hardware will not work, but you always will have this system and you will be able to read and write to the flash.
Okay, but there is the other way, how to, maybe, just maybe, mm-hmm. we are transporting the firmware into our system. Is it possible? And then doing all the stuff like WinWork.
You're asking about a different way to transfer firmware from to download firmware?
I don't want to mm-hmm. create image this, but I want to grab the image from the device.
Yes.
And analyze it in
mm-hmm. It is possible, not very easy. I was looking for the command to do this in U-boot, but as I found is all versions of U-boot that I had, there is no command to. I haven't found the command to transfer the file using Kermit protocol from the firmware, from the device to our serial console. But I think there are some versions of U-boot that have such command. So you can just the copy command and copy flash, the whole flash to your device using Kermit.
Okay, thanks.
Hi, I would like to ask you how your zodiac sign influenced your career.
I don't think it influenced in any way. Okay, so I think that's all. Thank you.